Welcome to Section 2 of Introduction to Image Processing. This section introduces operations for controlling brightness and color in an image. So to get started, here is a sample image. There are lots of things we might do with this image. One operation is making the image lighter, which is done here using a function called lighter, which makes the image a little bit lighter. The lighter function takes a second argument that specifies how much lighter to make the image. This shows the lighter function used with that second argument set to 1/3, which is the default. And this shows the effect with that second argument set to 1, which makes the image quite a bit lighter. A convenient way to see the effect of variables like the second argument in the lighter function is to write a short manipulate program to provide interactive sliders for adjusting the variables. For example, this program uses manipulate to get a slider for adjusting the second argument in the lighter function. That second argument ranges from 0 to 1. 0 leaves the image unchanged, and 1 makes the image quite a bit lighter. The lighter function works by taking the numbers that are used inside the computer to represent the image and making those numbers bigger. The set of numbers that represent the image is called the image data. The image itself is an array of points called pixels. The image dimensions function shows that this image is a 182 by 128 array of pixels. Each pixel is represented in the computer by a set of numbers called the pixel value, and the array of pixel values is the image data. This input uses the image data function to show the image data for this image. The second argument in the lighter function specifies the fractional increase in those numbers. This shows the image data after applying the lighter function with second argument 1. Comparing the first few numbers from the original image with the first few numbers from the lighter image shows the bigger numbers in the image data for the lighter image. Like the image data is an array. For this image, the image data is an array with dimensions 128 by 182 by 3. The dimension 3 is there because in this image there are 3 numbers in each pixel value, and the other 2 dimensions give the height and the width of the image. One thing to notice here is that the height and the width dimensions for the image are given in the opposite order. That difference is just a matter of convention. In images, it is conventional to give the number of columns first, and in arrays, it is conventional to give the number of rows first. This difference is generally not a big issue, but it is something to keep in mind when working with the image data. Even for this relatively small image, there are about 70,000 numbers in the image data, which is, of course, a lot of numbers. It is easier to make sense of those numbers by zooming in on a more manageable piece of the image. Here is a piece that is basically another image consisting of a 2 by 2 array of pixels. The image data for that image shows the 2 by 2 array of pixel values. In this image, each pixel value is a list of 3 numbers that specify the color of that pixel. This image uses what is called the RGB color space, which means that the 3 numbers in each pixel value give the amounts of red, green, and blue light to mix together to get the color of that pixel. You can use the image color space function to find out the color space of an image. The color space for this image is RGB. The numbers in the image data all fall between 0 and 1, with bigger numbers indicating more light. If the lighter function is applied to make the image lighter, then the numbers get bigger. Several of the numbers in the result there are set to 1. The numbers are limited to the range from 0 to 1, so if making an image lighter would make a number bigger than 1, then the number is just set to 1, which indicates the maximum amount of that color. Another important characteristic of these numbers, which will come up again in a later section, is that the numbers for this image are stored in the computer as 8-bit computer bytes. A computer byte is made up of 8 zeros and ones. As a binary number, the 8 zeros and ones correspond to an integer from 0 to 255, so the native form for the numbers in the image data is actually integers from 0 to 255. This form of the numbers can be seen by including automatic as the second argument in the image data function. Those integers are also the values that are displayed when using the interactive coordinate tool to inspect individual pixels. For example, clicking on the image and selecting the coordinates tool and positioning the cursor over the image shows those same integers. For convenience in applications, it is common to divide all of those integers by 255 to get numbers that range from 0 to 1, which is what happens when the second argument of image data is omitted, but the underlying numbers are still integers between 0 and 255. The type of numbers used in the image data is given by the image type function. The image type for this image is byte. Other image types and some consequences of image type will be discussed in a later section. Returning now to operations on images, there are of course lots of other operations besides making an image lighter. For example, this input uses the darker function to make the image darker, which works by making all of the pixel values smaller. Like the lighter function, the darker function takes a second argument. Here is a manipulate for adjusting that second argument between 0 and 1. 0 leaves the image unchanged, and 1 darkens the image all the way to pure black. Another common operation is negating an image, which is done here using the color negate function. The result is a negative of the original image. Color negation works by subtracting each pixel value from 1, assuming of course that the numbers in each pixel value have been normalized to fall between 0 and 1. For example, here is an image that consists of a single red pixel. The image data for this image has the single pixel value 100, indicating the maximum amount of red light, and 0 for the amounts of green and blue light. The color negate function gives the negative of that image with a color called cyan, which is the complement of red. The image data for that image has the single pixel value 011, which is the result of subtracting the 100 pixel value from 1. There are many common color spaces besides RGB. One color space is the grayscale color space, which is used for black and white images. This input uses the color convert function to convert the color image into a grayscale image. Zooming in as before on a piece of that grayscale image and applying the image data function shows that each pixel value is now a single number rather than a list of 3 numbers. In the grayscale color space, that single number gives the brightness of the pixel on a scale from 0 to 1, with 0 being black and 1 being white, and other numbers used for other shades of gray. Sometimes it is useful to apply some specific custom operation to each pixel value in an image. One way to do that is with a function called image_apply, which works by applying a specified function to each pixel value. For example, here is a function that multiplies its argument by 2. The image_apply function can then be used to apply that function to each pixel in an image, which makes the image lighter. Multiplying each pixel value by 2 is basically what happens when the lighter function is used with a second argument of 1. Another operation that can be easily programmed using image_apply is color negation. Here again is the color negation example. If the pixel values have been normalized to fall between 0 and 1, then color negation is done by subtracting each pixel value from 1, which can be done using a function like this one, which subtracts its argument from 1. Applying that function to each pixel value gives the color negative. There are many other things that can be done with color. For example, one way of converting a color image to a grayscale image is to apply the mean function to the RGB pixel values, which replaces the 3 numbers in each RGB pixel value with a single number, and that single number is then automatically treated as a pixel value for a grayscale image. That's not quite what the color convert function does, however. Here again is the result from the earlier grayscale conversion, which gives slightly different shades of gray. The difference isn't dramatic, but the green parts of the image, for example, are a bit lighter. That difference happens because the color convert function actually does an operation more like this one, which gives a weighted average of the red and green and blue pixel values. The weighted average is used mostly because human eyes are more sensitive to certain colors. Human eyes are more sensitive to green than to blue, for example, so in converting to grayscale, more weight is given to green than to blue. Before concluding, and to put the examples from this section in some context, an important feature that all of the operations in this section have in common is that they all work by operating separately on each pixel. Operations that work that way are called pixel-wise operations or point-wise operations. There are lots of other image operations that operate on more than one pixel at a time, such as operations called neighborhood operations, where the handling of each pixel depends on nearby pixels. A simple example of a neighborhood operation is blurring an image, which works by replacing each pixel with a weighted average of the colors of nearby pixels. Various neighborhood operations will come up in later sections. That's the end of the examples for this section. To summarize, here is some of the vocabulary from this section. This section introduced some common pointwise image operations and reviewed a few basic concepts in digital image processing, such as the notion of a pixel and an array of pixels and pixel values, and the RGB and grayscale color spaces. The next section continues the review of concepts in image processing and introduces image histograms and more pointwise image operations.